Hello and welcome to Module 11 of Three-Dimensional Dynamics. Today's learning outcome is rather interesting. We're going to develop the equations of motion for a particle close to the Earth, where we're now going to treat the Earth as a rotating reference frame. We often treat it as inertial, but it's not truly inertial. And then we're going to do a real interesting problem next time once we have an example, once we have developed those equations of motion. So here's our situation. We have the Earth as a moving reference frame. Now, certainly this is not the scale. The Earth is rotating with a constant angular velocity, omega. The radius from the center of the Earth out to a moving reference frame is the distance r, and then we have little r out to a point or a particle close to the Earth's surface. And so we're going to fix our inertial reference frame at the center of the Earth, and it's not going to turn with the Earth, but we are going to embed or kind of weld a moving frame turning with the Earth. And so let's look at this with an example. Okay, so here's a model of my Earth. The Earth is rotating with a constant angular velocity, omega, and then the fixed frame is going to be at the center of the Earth, with its origin at the center, and it's not going to rotate at all. The moving frame is going to be embedded with the Earth and turning with the Earth. And so in that case, we have our little y-axis in this direction, our little z-axis in this direction, and the x-axis is pointed back towards me as it rotates with the Earth. Okay. So this is a very similar situation to the generic situation we developed with the hang glider. In this case, the inertial frame F is actually the center of the Earth, okay? And frame B, which was the car before, the moving frame, is now embedded to the Earth out here at this point. And then point P is our particle looked at from both frames. And we came up with the accelerations expressed in those moving frames of reference, and this was the equation that we came up with. And so now if I know the acceleration of point P, just as a review from my 2 dynamics course, how can I relate that acceleration to the forces acting on the particle? And what you should say is we just used Newton's second law. The external forces acting on the particle is equal to the mass times the acceleration of the particle. So I can substitute now the acceleration of P in here, and this is the result I get. As far as the external forces are concerned, I could have a vector of forces, a vector force with x, y, and z components. I have the minus mgz, or minus mg in the k direction, is the gravity force directed towards the Earth's center, and then mass times the acceleration expression. And so the first thing I want to look at in this equation is this term r double dot. Now r is the position vector from the center of the inertial frame out to the origin of the moving frame. And so we want to find out what the acceleration is of O prime, or R, capital R double dot. So our next step is to find the acceleration of the origin out here, O prime. And to do that, we're actually going to set up another set of 2 frames. This time I'm going to have my inertial frame again at the center, but I'm going to put another frame, frame C, a moving frame, which is also at the center but turning with the Earth. And so let's look at that situation over here. So in this case, I want to find the acceleration of the O prime point out here, which is R, capital R double prime. And so the inertial frame, again, is fixed at the center, not turning. The rotating frame in this case, frame C, is at the center, but it's rotating with the Earth. Okay, so in that case, I can write the equation of the acceleration of O prime with respect to F using frame C as the rotating reference frame or moving reference frame. So my first question to you is, given that situation, what is the acceleration of point O with respect to F? And you should say 0 because O and the moving frame and C, the origin of the moving frame C and the inertial frame are right on top of each other, so there's 0 acceleration. What about the acceleration relative to the moving frame of point O prime? What is that? And again, you should say that that's 0. Because if I'm in the center of the Earth and I'm rotating with the Earth and I look at this point O prime out here, when I'm rotating around, from my reference, O prime is not moving. It doesn't have any velocity and it doesn't have any acceleration relative to me. And so that means a rel is equal to 0. Since the Earth is rotating with a constant angular velocity, alpha is equal to 0, and we also already said that vrel is equal to 0. And so this equation reduces down to what's shown here. Now, this is back to our original situation where I had my inertial frame at the center and frame B embedded at the Earth. What I want to do next is I want to compare the angular velocity of B with respect to F and C with respect to F. What's that relationship equal to? And what you should say is that the angular velocity of both of those moving reference frames are the same. And so let's go ahead and look over here again. So if I have a frame out here, embedded out here, and it turns with the Earth, that's going to be the same as, I can't get this frame inside the ball, but if it was inside the ball and turning with the Earth, they would both rotate with the same angular velocity. And so I can therefore write this equation just by substituting omega b with respect to f for omega c with respect to f. Okay, and so here's where we're at as a recap. I've got the acceleration of p with respect to my inertial frame. I know Newton's second law. I substituted it in. I looked at this first term, which was the acceleration of r double prime, capital R double prime. I found it to be equal to this. And so I can go ahead and substitute that in. And I may go a little quick here on my equations, but you can always stop the video and make sure that you can see how each step takes place, because it's fairly straightforward algebra. Okay, so here's where we're at. Now I know that r from my little reference frame is just some distance in the x, some distance in the y, and some distance in the z direction. vrel from my moving reference frame B is going, it can have a relative of velocity, and it can have a relative acceleration, point P, with respect to my moving frame here, this particle next to the Earth. So this is the expression for vrel. This is the expression for arel. And finally, again, I know that the Earth is rotating with an angular acceleration that's 0. So it's got a constant angular velocity. And so here is the result that I get. Again, if you substitute these in, all right? And so here again is that same result. Now let's make some important assumptions. I said that this was not to scale at all because this particle is very close to the Earth. The radius of the Earth is obviously very large, and so little r is much, much less than big R, which means I can cancel out little r or neglect it. I know that my force, external force acting on my particle, can have x, y, and z components, and so I can substitute that in here. I also need to have omega b with respect to f in my little reference frame. Well, my moving reference frame. I see that omega b with respect to f, that's the rotation of the Earth, is omega in the big J direction. And so what I want you to do now is change that to the little I, J, K coordinate system. And you've done this several times before. Hopefully it'll be straightforward, and come on back and see how you did. And so this is the results you should have arrived at. Omega J, the big J component is cosine theta in the little j direction and sine theta in the little z direction or k direction. Okay, so now I can substitute all of this in. Again, this will go in here, here, and here. And the result I get is f x I plus Fyj plus Fzk minus mgk equals now m times, okay, omega b with respect to f, we just found to be omega times cosine lambda j plus sine lambda k. That's crossed with omega again, omega b with respect to f, which is omega cosine lambda j plus sine lambda k. And that is crossed with r. Big R. Big R is big R in the little k direction. And then I've got plus 2 times omega. Omega again is omega times cosine lambda j plus sine lambda k. And that's crossed with my relative velocity, which is x dot I plus y dot j plus z dot k. And then all I'm left with is my relative acceleration, which is plus x double dot I plus y double dot j plus z double dot k. And that's the expression. And I'll write that out. Let's clean that up here, and this is the result you get. Now I'm going to go through, again, a couple steps. Mathematically, it's fairly straightforward algebra. You can stop and watch as I go through these 2 steps to reduce this. The result I get is here. And now my equations of motion for the particle can be found by equating the I, j, and k components. So if you equate the I components first, you find the acceleration equation of motion for x double dot. If you equate the j components, this is your next equation of motion. And if you equate the z, or the k components, this is your final equation of motion. So these are the 3 equations of motion for motion of a particle close to the Earth's surface. And we'll use this theory, with a really interesting example in the next module.